Hello, everybody. Welcome to Module 7 of Water 290, Santa Fe Community College. Tonight, we're going to discuss sedimentation and flotation. Most of the material is going to come from the New Mexico Environment Department Study Guide, Chapter 6. And as you recall, we may have discussed, or we did discuss some of these topics in Chapter 3, Primary Treatment, the clarifier section in the Ragsdale Manual. But like I said, I want to make sure that I cover all material for you that could show up on the exam. So we're going to cover Chapter 6 of the Environment Department Study Guide. And the major topics we'll be discussing in this lecture include core mechanics of settling and floating solids, some math formulas that you're going to need to know for operational control, and the math that we'll discuss and that I'll be giving you on your assignment will touch levels 1, 2, 3, and 4. We'll also discuss a couple of alternative systems, mainly Imhoff tanks, which are no longer being built but are of some historical relevance, and you'll still find some here and there in rural areas, as well as combined units, which are also known as package plants. You may have heard that term, and that's basically a combined unit. We'll go over this a bit later. Sedimentation notes for your certification exams, they run through every single level, including the small wastewater and small wastewater advanced. This is a crucial topic, and it's one that you should be prepared for. But again, recall for level 3 and level 4, the main stuff you're going to see is the activated sludge work. For level 2, you'll see a lot of ponds, but you will see this material in all 4 levels of all 4 exams. So this is important. Please do your readings, your homework, and watch the lectures, and you'll get through it okay. So this is a cross section of a clarifier sedimentation basin. And the one thing I'll point out is a clarifier really is just a sedimentation basin. It's where solids settle out from a liquid waste. The suspended solids will settle out into a primary clarifier, and although the secondary clarifier does have some biological activity taking place, it is still a settling basin or a sedimentation basin. So when you hear clarifier, it's synonymous typically with a sedimentation basin. Okay, what I'd like you to do as part of your studying task and getting ready for your exam, take a look at Ragsdale Manual Chapter 3 or NMED Chapter 6. They're going to talk about the different zones within clarifiers, and take this diagram, this slide, and draw in the different zones on the schematic. And that'll help you figure out and have a good way to just explain and answer questions on the different zones within clarifiers and sedimentation basins. And you will see this within the level 3 and level 4 exams. You're also going to need to know the components and their functions. So the other thing I would do just as part of your studying efforts, here is table 6.2, the purpose of clarifier, parts of a circular clarifier. And I would look at these components and I would match them up to the diagram on the previous page. And what I would do is I would read through the table and I would just put the numbers by the location of each of the components on that schematic, on that drawing, and then just try and understand how the process is working or how the piece of equipment is working, because you are going to get questions on these. It'll basically say, okay, what does this part do? Or you'll have to do troubleshooting or what have you. One favorite that they ask about is what happens with what causes an uneven sludge blanket, or what are the indications of an uneven sludge blanket. And those are things you should be able to look at, including the torque indicator up on the catwalk there for the motor that's moving that sludge rake around. Okay, so please do take a look at this and please match it up with the diagram on the previous page. You will get a few questions here and there on your different levels. Okay. Here's a rectangular clarifier, and as you recall, we talked about this in Chapter 3 of the Ragsdale Manual. So be able to discuss what the parts are and label the parts if you need to, and understand what each of the parts do on this diagram. And the next table on the next slide is going to show you what each of these parts do, and that's out of Chapter 6 of the NMED Study Guide. But again, whether you're more comfortable with the Ragsdale Manual Chapter 3 or NMED Study Guide Chapter 6, look at the parts, look at the components, and know their purposes, okay? As well as be able to label or describe the different zones in each of the clarifiers. That is something you do need to know for your exams, okay? And I just wanted to call that out. And if you want to print a full page slide, at least this is blown up for you and have at it. I think that'll help you with your study efforts. And this is table 6.1. It's the rectangular sedimentation basin or clarifier and the parts. You'll notice that I took number 8 and I put it on its side here, which is the sump. And I did that because it was just really difficult to fit the whole table in without cutting part of it out. And it wouldn't have been easy to read had I left it vertical. So I rotated it. It's now horizontal here. But please do take a look at that and please match it up and do some studying with respect to the previous figure on the previous slide. Okay, so purposes of sedimentation. Okay, so recall that in our sedimentation basin or our primary clarifier, what we're trying to do is we're trying to get the heavier settleable solids to settle down into the sludge blanket, and the organics, the fats, the oils, the greases, if you will, we want them to float to the top where we're going to have a scraper, and direct that into a trough, a scum trough or a scum box, okay? We do this, recall, by slowing down the velocity of that wastewater. So recall that we have a velocity of 2 feet per second in our collection system for wastewater, which makes sure that solids don't settle out in our wastewater collection system. And when that hits the preliminary or pre-treatment phase with the bar screens and what have you, we're slowing that wastewater down from 2 feet per second in the collection system to 1 foot per second in the preliminary treatment, to go through the bar screens, to go through the commutator, and to go through the grit washing or grit removal system. And then when we hit the primary clarifier, we're significantly reducing that. And the whole idea here is we're lowering that wastewater speed or that velocity of that flow to let those heavier particles drop out. That's what a sedimentation basin does. That's what the mechanics of sedimentation do. And we're eliminating those heavy organic and inorganic matter and settlable solids just by gravity. So we don't have to expend a whole lot of energy. We're just letting that waste stream hang out in a nice settling still pond until that heavier stuff is allowed time to drop out. And that's what we would call detention time, the time that it takes for that wastewater stream to pass through a basin or a clarifier. That's detention time. Okay, so we also, in addition to letting gravity take care of those settleable solids, that heavier organic and inorganic material, and settle to the sludge blanket, the organics, the fats, oils, greases, the lighter stuff with a specific gravity less than 1, lighter than water, is going to rise to the surface, and we're going to skim that off. So we've got 2 separation mechanisms going on here. We've got sedimentation allowing those heavier particles to float to the bottom, settle out, and that those particles have a specific gravity greater than 1, greater than water. They're heavier than water, which lets them settle out. The lighter stuff, specific gravity less than 1, lighter than water, floats to the top. So those are the 2 mechanisms, sedimentation and flotation. Okay, for class 1 and 2, I'm going to try putting these little exam hints and guides and targets for you and study tips on some of the slides. I hope they help. If they help, let me know. If you find them annoying, let me know that as well, and I'll stop doing it, okay? But for class 1 and 2 or levels 1 and 2, expect conceptual questions on why we have to drop the velocity in that clarifier. And again, what we're doing is we're slowing down that flow velocity so the heavier organic and inorganic settle out and the lighter material rises. That's why we're slowing it down. We're giving that mechanism some time, detention time, so those 2 processes of sedimentation and flotation take place. Okay. This is something you will see on a level 1, level 2 exam. You may even see it on a level 3, level 4. Um, and that's how to calculate the clarifier efficiency. Uh, so what this does, this efficiency measures the percentage of the pollutants that we successfully remove in the clarifier. And the formula is simply the efficiency of your clarifier is just your influent, what's coming in, the concentration coming in, and you subtract the effluent, what's leaving, you subtract that concentration, and you divide by the influent, and you multiply that by 100 to get a percentage. And you're typically going to look at efficiency with respect to BOD, biochemical oxygen demand, and total suspended solids. That's what you're typically going to measure the efficiency removal of in your clarifier. Okay, so the concentrations we're talking about here will be milligrams per liter of BOD coming in, milligrams per liter of BOD coming out, or it can be this total suspended solids, milligrams per liter coming in minus milligrams per liter going out, divided by the incoming concentration. So there's this phrase you're welcome to memorize, or just kind of commit to memory if this is giving you a hard time, or as you initially do it. And it's basically in minus out divided by in minus out divided by in, multiplied by 100, in minus out divided by in. That's going to give you the efficiency, okay? Um, Here's the other thing I want to point out. While I'm encouraging you to understand the math formulas, please do not think that you have to memorize all these formulas. You don't. You are going to be given a formula sheet, and I want to say that thing's like 8 to 11 pages long. You're going to be given a formula sheet for all these relationships they want you to know and be able to use on your exam. But something like this, you should be able to understand what's going on, but don't sweat memorizing formulas. I hope that does help and put you a little bit at ease, but you do want to understand what you're looking at. Okay. So typical clarifier efficiencies with respect to total suspended solid removal, you're looking at 40 to 60% of TSS being removed by a clarifier. For BOD, you're going to remove 25 to 35% of what's called that organic loading from the influent or the BOD coming in. You're going to reduce it by 25 to 35% from what's coming in to what's going out. And you'll also have a visual indicator here. So if the clarifier is performing really, really well, you're going to be able to visibly see the downstream organic load or the clarity of that effluent in the secondary biological processes. You're going to notice that it's a lot less murky or brownish colored or grayish colored. That reduction in color will happen as you go through the primary clarifier. So with the exam target, this is for all levels. Those exact percentages for total suspended solid removal from a clarifier, 40 to 60%, and 25 to 35% in BOD removal, those are something on all different levels that you should be able to remember and understand. Okay, all different levels. So some design factors for clarifiers that you should understand, should be able to talk about and understand and discuss. And if you can do that, you're going to be able to answer the questions on the certification exam. So with temperature, recall that in chapter 3 of the Ragsdale manual, we said that temperature differentials, they can cause density currents. They can disrupt settling patterns. What it means is you're going to have maybe a different flow or different flow pattern within the clarifier if there's a wide differential or variation of temperatures. Okay. You can also have what's called short circuiting. And short circuiting is basically wastewater skipping the intended uniform path, and it goes from the inlet of the clarifier to the outlet too quickly. So the wastewater doesn't have time to allow the heavier inorganics and organics to settle out and let the lighter organics float to the top. So short circuiting is something you should know for all 4 levels of the exam. And you should be able to discuss it just as matter of course as a wastewater or water professional. Okay. And detention time. The average time that that wastewater is going to spend in a clarifier, the primary clarifier, 1.5 to 2.5 hours. That's for any sedimentation basin. Okay. So for levels 2 and 3, you want to understand, particularly levels 2 and 3, you want to understand the cause and effect of short circuiting and how density currents form, because you're going to see some of those questions on your level 2 and level 3 exams. Okay. Couple of side notes. I inserted a few side notes here because I looked and said, you know what? We haven't defined a few things, and although I'm talking about things, and I think they're fairly clear, I still want to take a moment to make sure you guys understand what I'm talking about when I mention a certain term. So let's talk about detention time. Let's define it, and then let's define calculations on it. Okay. So the definition of detention time, you can also call it hydraulic retention time or hydraulic residence time. That's basically the average amount of time that a volume of wastewater, whether it's a drop or a gallon or a bucket, is going to spend inside a specific portion or treatment process. In this case, a clarifier, or a tank or reactor or a basin. In this case, like I said, it's the clarifier. The idea is that when we have a detention time, we want to meet that detention time to make sure that the water and its contaminants, its organic loads, settlable solids, what have you, that they're hanging out enough or long enough for the settling or floating process to take place, or any other process we may be looking at. Okay, so we make sure that the wastewater is in the process, whether it's a physical, chemical, or biological process like settling, disinfection, or metabolization of the organic matter by microbes. So the wastewater is going to hang out long enough for whatever process we're subjecting it to occur. And it's important because if that detention time, or the amount of time the wastewater spends in a certain process, is too short, well, then that process isn't going to be complete. And the water quality or the wastewater effluent quality leaving that process uh, isn't going to be what it needs to be for the other processes to be effective down the line. And the idea of it being too long is, if it's too long, the entire facility is just kind of standing still. So we're not operating in an efficient, cost-effective manner. So there are downers to detention time being too short, which is the process doesn't have time to fully take place. And there are times where detention time being too long is a negative, because in that case, we're basically keeping our entire process or facility idle because of a longer than necessary detention time in a certain process. This is the formula. Okay. Your detention time T is the retention or detention time for your process. It's equal to the volume of your basin or your tank or whatever vessel you're using to conduct a process, divided by the flow. It's called volumetric flow rate, but it's the flow uh, of the influent, the wastewater coming into the system. So detention time is the volume of your basin or clarifier divided by the inflow of the wastewater coming in. And you want to make sure, for example, that your volume units, let's say they are in gallons, well, then the flow has to be in gallons per minute or gallons per hour, or typically gallons per day. And if you're given a flow rate of millions of gallons per day, we'll talk about how to adjust that. Okay. But you can't use volume in cubic feet and then divide it by a flow rate of gallons per day or millions of gallons per day. The volume unit has to match up with the flow unit. They both have to be in gallons or millions of gallons or cubic feet, whatever it may be. Okay. Typically it's gallons is what you're going to want to use. So as I mentioned, the units for the volume and flow rate got to cancel each other out. That's why they got to be the same. Because if you have a cubic foot divided by a gallon per day, the cubic foot can't cancel out the gallon on the denominator, the gallon per day. So you're going to end up with volume divided by flow rate, you're going to end up with a unit of time. Whether it be days or hours, that's what you're going to end up with. So here's a few examples, and I mixed up some metric system stuff in here. So if you're not comfortable with that, don't sweat it. The only thing you're going to see in the metric system is milligrams per liter, and we'll describe how to deal with that in something called the pounds formula a little later on. Okay, but if volume's in cubic meters, then flow's got to be in cubic meters per time or cubic meters per hour. And if that's the case, volume's in cubic meters, flow's in cubic meters per hour, then the time's going to be in hours. If volume's in gallons and flow is in gallons per day, the detention time is going to be in days. Okay. Keep in mind, time is equal to volume divided by flow. Okay. So if you see volume in gallons and flow in millions of gallons per day, the time is going to be in days, but we've got to get this this MGD unit to match up with the gallons unit. Okay, and we'll look at this on the next slide. So for an example, if you have a tank volume of 800,000 gallons, that's your V. Your inflow rate is 1.2 million gallons per day, MGD. Okay, the first thing you got to do to get gallons and millions of gallons per day in the same unit is you convert the 1.2 million gallons to 1,200,000 gallons per day. Okay, 1.2 MGD is equal to 1,200,000 gallons per day. And then you can use this formula, detention time, T, is equal to volume, which is V, divided by flow rate. And we plug in the 800,000 gallons as the volume. We plug in the 1,200,000 gallons per day as the flow rate, and those gallon units are going to cancel out. So we're left with units of 1 over 1 over day. So when you do that, you're going to be left with units of days. Okay. Now, here's the thing. I said, well, we're going to convert that 0.67 days, 800,000 gallons, divided by 1,200,000 gallons per day. That's detention time is equal to 0.67 days. But most people don't think in fractions of days, so we would convert that to hours. And we would do that by saying 0.67 days, our detention time, multiplied by 24 hours in one day, and those units are going to cancel out. And we're left with units of hours. So 0.67 times 24, that's 16 hours. Okay. So step 4 is I'm saying that's optional, and it's optional, but it's optional here because I didn't tell you what units to end up with. But on the exam, it's going to tell you what units just by listing the answers in multiple choice format, and you're not going to have to fill in numbers on your exam. You're going to have multiple choice selections, even for math problems. But that's what's going to tell you what units to go to. So make sure you read the question, and then you look and see what the responses are. Okay, not necessarily the numerical part, but the units. Okay, so here's what I'm going to tell people, and I always advise people that are going to take these exams with respect to math problems. Here's what I tell them to do. First thing you should do is read the problem. The second thing you should do is read the problem again, and then write down what you are given on one side of your scratch paper. In this case, we were given volume equals 800,000 gallons. We were given flow rate, or Q, is equal to 1.2 million gallons per day. And by writing that out, you should have looked and said, okay, 800,000 gallons and 1.2 MGD. I've got to convert the 1.2 MGD into 1,200,000 gallons per day. And then you do the math. You take that ratio, you do that division, and you look at the units, and then you'll come out with days if you do that correctly. But if the answers are in hours, then you got to convert that day or fractional day into hours by multiplying by 24 hours per day. So that's what I do. I read the problem, I read it again, I write down what I'm given, and then I write down what I'm being asked for, and then I go from there. That typically saves a lot of time and keeps you fairly organized if you do that. Okay. So the takeaway, we're going to do this for each of the math problems in this chapter, and I hope you get in the habit of thinking, well, does that make sense? Do I meet requirements? Does it make sense? Those are some reality checks. Okay, so the wastewater in this case spends an average of 16 point hours in the clarifier. Well, that's enough time when we think about it for those solids to settle out before the wastewater moves to the next treatment stage. So yeah, it makes sense. Now, if we came out with 120 hours, yeah, that's a little too long. If we came out with 1 hour, zero point 0.5 hours, that might be too short a time. Okay, so conduct a reality check by saying, does this make sense? Okay, so there are three clarifier metrics or ways to measure clarifier performance. That's a metric. How do we measure the performance of something? Well, what we typically do is we take a look at three different criteria or metrics for clarifiers. We look at a weir overflow rate, which is the gallons of water passing over each foot of the weir, the outlet weir of that clarifier on a daily basis or daily time frame. We look at something called the surface settling rate, which is also called the surface loading rate, and that's the amount of gallons that are passing through each square foot of cross-sectional area of our clarifier. The tank surface area is the top, the cross-sectional area, okay? We also look at solids loading, and that's the total pounds of dry solid applied daily per square foot of clarifier area, okay? So a note here, a study tip, we're dealing quite a bit with circular clarifiers. Matter of fact, that's typically what you're mainly tested on. You can occasionally and will occasionally see a rectangular clarifier, but to get the surface area of that, that's just length times width. That's pretty straightforward. Uh, or you're just looking at the perimeter of the, or not even the perimeter. You're looking at a certain weir length for the weir overflow length, and it's something you'll be able to see pretty quickly. But a study tip is you really got to know how to calculate the surface area of a circle, pi r squared, and the weir circumference, which is the distance around a circle, the perimeter of the circle, okay? You got to be able to do that in the exam. You got to know that like the back of your hand, and I'm here to tell you right now, that pi r squared, I'm going to show you a different way of calculating the surface area of a circle. It's going to save you a lot of time, okay? And what I'm also going to tell you is those three metrics, I've got a separate lecture on those because it would have taken, oh God, a couple hours of a lecture to get through those plus the sedimentation and flotation material. So I've got a separate lecture for those three items, the weir overflow rate, the surface loading rate, and the solids loading rate. I've got a separate lecture that I'll record and that'll walk you through how to calculate those things, okay? So another thing we want to look at, we talked mainly about primary clarifiers, but let's look at secondary clarifiers. Recall that a primary clarifier, the idea there is to let the heavier solids settle out of the wastewater stream and let the lighter organics, fats, oils, greases float to the top of the surface and get skimmed away. It's basically a physical type process, sedimentation, flotation. In a secondary clarifier, what we're doing is we are also adding in activated sludge or microbes that we've basically, and we'll discuss this in the activated sludge chapter, we've basically given them some oxygen. We've given them a surplus of oxygen, and we've made them very hungry to go metabolize that waste, the organics in that waste. So the secondary clarifier is a biologically driven process, okay? And we can have a couple of different ways of approaching this biological process. We can have a trickling filter clarifier, and that's basically, if you think about it, filter media like rock that we allow the wastewater to flow over. And what happens is on that rock or that filter media, and the reason I call it rock is I want you to get in the idea here that these are some rather large surfaces we want to deal with. It's not sand where we're trying to trap things. We want the wastewater flowing over the filter media, and it's got what's called this heavy sloughed biological biomass or humus, and it's on the media. And that's where the microbes that are going to digest the waste and metabolize the waste, that's where they're hanging out. Think of it again as a bunch of big rocks or medium-sized rocks in a filter bed covered with this organic slime. That organic slime has the biomass that is metabolizing the waste. And as we pour that wastewater over it, that's what that biomass is doing, okay? We also have an activated sludge clarifier, and that's similar to a certain extent to a primary clarifier, only we're introducing, uh, like I said, heavily concentrated dissolved oxygen into our wastewater along with microbes, and we let them hang out in that secondary clarifier where those microbes are going to chomp away at that waste. Okay, so this, what you're looking at with an activated sludge secondary clarifier, we're dealing with a volume of light, fluffy, flocculated solids. Think of these little tiny, very light mud snowflakes, okay, that are accreting together and falling to the bottom of that clarifier. And what we're doing is we are in the entrance, the inlet of the secondary clarifier, we are taking activated sludge that we've pulled off that sludge blanket that has organics and a lot of microbes in there, and we're returning that to the inlet or influent, mixing it with the influent of the secondary clarifier. So we're spiking it with hungry microbes. That's return activated sludge, or RAS. Okay, we're taking that as we pump the sludge blanket from the bottom of that secondary clarifier. That RAS portion of it is returned to the inlet of that secondary clarifier. And the waste activated sludge, well, that's just going off for the digester or dewatering, as we talked about in the last chapter or last module. So that's how we're controlling that sludge blanket at the bottom of the secondary clarifier. We're recycling the sludge with the microbes going to the inlet of the secondary clarifier, and then we're wasting the sludge to the digester and then off to solids treatment facilities, so that we don't have these mondo sludge blankets. And think about it. If we didn't have a way to waste that sludge, our pump wasn't, doesn't have a capacity, or sludge pump, to get rid of that sludge blanket, and our inflow of sludge or wastewater coming in is too high, or it's at a greater capacity than the sludge pump to get rid of that sludge and waste it, we're eventually going to have a pretty thick sludge blanket till it takes over that secondary clarifier and overflows. Okay, so we want to size the sludge pump at such a rate or such a size that we can easily deal with that sludge blanket without worrying about overflowing or accreting a very large sludge blanket by the amount of waste coming in or sludge being produced in the secondary clarifier. Okay, so for levels 3 and 4, these exams, they're going to ask you a lot of operational difference questions between a primary blanket and an activated sludge blanket. Be prepared to know the differences as well as management techniques for both a primary clarifier sludge blanket as well as a secondary clarifier sludge blanket. Recall that I told you on level 3, activated sludge is a huge portion of your exam. I want to say 30 to 40% of your exam. No difference with respect to level 4. Only thing is they're not going to tell you that because they already expect you to know it. Okay, so those are some questions you are going to see sludge blanket management on your level 3 and level 4 exams. Some safety rules and some clarifier maintenance rules. Okay, so you're always going to get safety questions. Every single level of these exams has a lot of safety questions. And by a lot, I mean maybe anywhere between 7 to 10 to 12 questions on the exam that directly relate to safety practices, to safety programs, what have you. Those are easy points. Don't give those up. study the safety chapters. You can read through those without me having to lecture you on them. And they are things that I think if you work up at land or you work in a water wastewater plant in a utility, um, that's stressed daily. If management or your supervisor catches you violating a safety procedure, you're going to hear about it. You're going to hear about it pretty doggone quickly and pretty loudly. And but these are, with respect to these certification exams, these are easy points. Make sure you study up on those and you don't lose any points. Okay. So, with respect to clarifiers, we have these catwalks we've been seeing on the primary and secondary clarifiers, right? Well, any algae buildup there, any oil or grease that accumulates there, you can have the whole slip, trip, fall hazard there. So you want to keep those free of not just debris, but of any of these materials that could cause it to be rather slick as a walking surface. You're also going to want to make sure that with your any of your mechanical equipment, that it's lubricated and it's aligned. Whether it's the sludge collector arms or the skimmers, nothing is going to ruin your day more than hearing a screeching halt of metal against metal. If you don't have enough lubrication, or if something's misaligned and just starts rubbing metal against metal, and you're going to break something, it's probably going to be expensive and hard to repair. Okay. Confined spaces. So the sludge pits, the sumps, and the drained clarifier floors, those are what are called permit controlled confined spaces or permit required confined spaces. Okay. You're not going to go in there unless you have a permit to do so. And you're going to have some safeguards, and we'll talk about this in the safety chapter. But those are permit required spaces to get into confined spaces. So again, these are easy points. Remember basic OSHA rules. If you are working on drive gears, apply lockout tagouts. Understand what lockout tagouts are, and I think all of you do by now. Read Ragsdale Manual Chapter 16 and Chapter 2 of the NMED Studying Guide before the class lectures. We'll have those towards the end of the semester. Those are easy points on the exam. Every level's asked that material. And now here's the thing. You may have heard some people say, you know what, I missed my next level up on my exam by 1 or 2 points. Like if I'd gotten 1 or 2 questions right, additionally right, I would have passed. And then if they look at their safety diagnostic, if they missed anything, that's where they could have passed. So like I said, these are easy points. Don't give those up. Don't blow them off. Pick up the easy points. Do yourself a favor. Make life easy on yourself for these exams, okay? These combined sedimentation digester units, so you have a sedimentation basin and a digester in one unit. That's called a package plant, is what it basically is. So they're compact package treatment plants, and they have a small clarifier directly over a sludge digester. Okay, so the idea is these small localized communities, even remote schools, boarding schools, campgrounds, like the Glorieta Conference Center out east of Santa Fe. Some small communities, they'll have package plants. And again, all that is, it's a small clarifier over a digester. And the idea is to save footprint, to make life easy on them. And they don't have an overwhelmingly large inflow of wastewater, domestic wastewater. You're not talking in the millions of gallons per day range. You're talking, oh gosh, anywhere between 20,000 gallons per day all the way up to 150, 200,000 gallons per day, if that. So those are things you will see in your career if you stick around long enough. A lot of operators specialize in these smaller systems, and you'll see folks that'll start their own contract wastewater company where they'll contract with these smaller communities to go act as their operator of record and maintain and operate these package plants. And they are automated, but they still need somebody to check on them. You still need reports, you still need sampling, you still need permit reporting, reporting and compliance reporting. So there are people that'll pick up contracts to do these for these small villages and these small communities and schools. And it can be kind of lucrative without killing yourself. You know, it's a function of how much you want to do. As long as you have the right certifications, the small wastewater and small wastewater advance will help you with this if that's the route you want to go. Okay. Um, so the idea here is they're pretty efficient, and they are a lot more efficient and easier to deal with than larger septic systems or the bigger Imhoff tanks that we'll talk about in a little bit. Okay. And they're pretty effective. With respect to BOD, they'll remove 35% of the BOD load from the inlet, the influent to the effluent, the outflow. Okay. They'll take 35% of that BOD right away. They'll process that with suspended sediments from raw influent. They're going to take out 65% of those suspended sediments going through these package plants. So they are pretty efficient and they are pretty slick. Okay. So with these package plants that we've been talking about, influent to effluent. So how do we process the influent and discharge and get to the discharge of the effluent? Well, first thing is the influent's going to enter through a flow meter. So we're going to track and record the hydraulic loading. And all the hydraulic loading is, we've talked about this, used this term before. Hydraulic loading is the volume flow rate coming into the plant. What's the daily flow, million gallons per day, coming into your plant? What are you treating? And you are required to track that and record that. Okay. And the first thing that's going to happen is you're going to have the preliminary screening, the preliminary treatment. You're going to have a bar screen there, and those branches, those diapers, wipes, what have you, they're going to get captured so they don't go inside that basin or that clarifier, and they don't create a problem for your process. And that's going to be captured, raked up, and disposed of. So it'll get collected. It's raked out daily to make sure that that screen's kept clean. And then that's all taken to the landfill. Okay. The wastewater is going to come in near the surface of a circular influent well. That's the inlet. It's a circular influent well. And that influent well, just like with a primary clarifier, it's going to take that, well, it's a little different. Rather than taking it to the center of the primary clarifier in an activated sludge plant and sending it up, what's going to happen is that influent well is going to take it down, and it's going to let that settled wastewater move slowly towards the outer perimeter. So instead of going up and then spraying out over hitting a baffle and spraying down, it's basically going to flow downward initially, and it's going to flow outward just like the other clarifiers, the primary we talked about, will do. And that clarified liquid is going to overflow on the edge of that circular basin. You're going to have a weir, an overflow weir, and we'll take a couple of looks at a couple in just a bit. Or actually, we're going to do that in the weir overflow rate next lecture, where I describe the math behind it. We'll take a look at a couple of weirs and you'll see how that happens. But that flow, that clarified liquid or decanted or supernatant liquid, is going to go through that effluent weir and into a collection launder, which is just a small ditch or trench, a collector. And then that effluent is going to go to secondary polishing, usually an activated sludge plant or a pond, if you will. We talked about the ponds last lecture, so that's what you're looking at, discharge from a package plant heading to. Okay. Now, remember I told you we've got a clarifier in a package plant. We've got a clarifier on top of a sludge digester. So the sludge and digestion management, we're going to basically scrape the sludge, separate it, and dispose of it. So the settled solids on the clarifier tray, they're scraped just same method. We've got a rake, a scraper that's going to scrape it to the center of the clarifier on top of the unit, at the top of the unit, and that center slot is going to take that sludge and it's going to move it down to the digester. It's like instead of pumping it away, we're actually using gravity and that rake to send it to some slots where it's going to come down into the digester. And that we're going to have a sludge seal below that, and that digester gas, and it's going to prevent digester gas from going up into the clarifier. And that is what the seal is going to do, as well as any sludge rising going into that clarifier as well and causing us problems. So that's why we have a boot seal there. Okay, and in the digester, the we're going to have sludge there, and that sludge is going to be what's called subsurface, which means it's below the top of the sludge blanket. It's just going to be decomposed aerobically, so it's going to use dissolved oxygen, or the oxygen in that unit, to decompose in the bottom of the package plant, which is where the digester is. Okay, and that digested sludge, we are going to have a pump there, and we're going to pump it or have a gravity drain line and send it to some drying beds. So we are basically walking through a package plant like this. We've got the influent coming in, goes through the preliminary treatment, the bar screens, what have you. It gets applied to a clarifier at the top of the combined unit, where that settling occurs, takes place, and then the clear liquid, or the supernatant, or is decanted or flows over the weirs, and then the sludge gets raked to the center bottom of that clarifier on top of the unit, gets passed down to the digester. The sludge blanket is building up, and the microbes, using that dissolved oxygen, they're decomposing that waste, and then we pump it or use a gravity drain line to send that treated sludge that the microbes have chomped on and has decomposed. We're going to send that off to a drying bed. Okay, that's it in a nutshell. And here's where we're at. We're looking at the top here of the package plant. Okay, this is called the plan view, and you'll see it's circular. Okay, and you've got the inlet, and it's slowly moving around. It's just got a chain slowly moving that sludge rake around. And this is what it looks like from the side. You've got a motor, and that motor is turning that sludge rake. So we have wastewater coming in, and we're giving it time to settle out, and sludge builds up here. And as it builds up, it gets passed down to the digester. We've got our rake, that clarifier arm, it's a rake basically, and it's taking it down to the center to a tray where we've got a seal here, that boot seal we talked about, and we've got a squeegee here. We're moving that sludge down, and as the clarified or supernatant water, the liquid portion, is cleared out of those solids, it comes out and it flows over that weir on the sides into an effluent launder, which is just a ditch on the other side of the weir. Okay, and as I mentioned, we also have a digester arm. Well, I didn't mention this. We have a digester arm that's also making sure that sludge blanket is uniform. The sludge blanket is being decomposed, and as we need to evacuate it, we'll take it off from the bottom of the sludge blanket and send it to a drying bed. That's it in a nutshell. You have the clarifier up on top, and you've got a digester on the bottom. That's a package plant, okay, or a combined clarifier digester, clarifier digester, or a sediment basin and digester. Okay, that's what we're looking at here. So these are considered kind of package plants. There are other smaller package plants that do a little bit more than what we're seeing here, but you can call this a package plant. Okay. There's this thing called an Imhoff tank. Remember last time we talked about measuring suspended or TSS concentrations using an Imhoff cone? We're going to use that process of settling, or we used to use that process of settling in rural areas with what's called an Imhoff tank. And this, I call it historic because you'll still see some. We're not building anymore. Nobody says, "Oh my God, I got to have me an Imhoff tank for my new wastewater treatment scheme in a rural area." No, but there's still some out there, so we should know about it. So these Imhoff tanks, they're two-story combined system, and just like the combined sedimentation and digester unit we just looked at, they're going to have those two processes in a single footprint, so a single structure. And the top is the sedimentation. It's a settling area, just like we talked about with the package plant. And that's where the flow is going to slow down. And we've got a slot at the bottom of that clarifier or settling basin. And the sludge is going to drop down through a slot into the digestion area. And that's the lower compartment. And that's where those trapped solids, they're going to undergo not aerobic, which is the oxygen rich environment. They're going to get decomposed via anaerobic decomposition, which means there's no dissolved oxygen or oxygen present for this process. So that's the difference between a combined unit and an Imhoff tank. The big difference, the combined unit is going to have an aerobic process for decomposition in the digester. The Imhoff tank is going to have an anaerobic or lack of oxygen decomposition. Okay, and we've got a slot in there, and just like with the boot seal on the earlier combined unit, that slot's designed so that those anaerobic gas bubbles, they're not going to go to the upper chamber, the settling chamber, and create problems there. Okay. For small systems, and none of you in here are going to go for your small systems cert, which is fine. Particularly small systems, you'll get some questions on this. Class 1, you might get some questions on this, just one or two, not a whole lot. And they'll ask how that slot or baffle prevents gas bubbles from mixing into the settling water. And all you got to do is basically say it blocks the gas from migrating to the upper chamber. It's a seal. That's all it is. The design is a seal, just like the boot seal on the combined unit. Okay. And here's a schematic of an Imhoff tank. And, here's the idea here. You have your settling compartment. You've got a slot, which is where the sludge is heading to. It's leaving the settling compartment, it's gathering, and the slot comes here, takes it to the digestion compartment. Okay, and whoever the operator is can pump that out, the bottom of the sludge that's built up here. But look, we're having an anaerobic, lack of oxygen reaction take place here. So I misled you a little bit. It's not a gas seal. On an Imhoff tank, the gas is just vented off to the side, 360 degrees off to the side of the settling tank. Whereas with a combined unit, you have a seal. So in this case, the gas is going to go up. Here's your sludge blanket. And you're going to have gas that's going to be off-gassed through these channels. Okay, they're just collected. And in here, let's use brown in here. This is where your wastewater is coming in. Okay, and your sludge builds up, comes down, and forms your sludge blanket here. And we can take that sludge away via these removal lines. Okay, hope I didn't confuse you too bad. Like I said, for a combined unit, you got a boot seal. For an Imhoff tank, you have these chambers off to the side. Sorry, I'm a little discombobulated today. Sorry about that. Okay. Side note. So I mentioned in an earlier slide, we're using decentralized wastewater treatment. And I did that without telling you what decentralized and centralized wastewater treatment is. And I looked through the manuals, both Ragsdale and the NMED study guide. The Ragsdale manual doesn't really use centralized versus decentralized. The NMED study guide does, but they don't really tell you what the difference is. Well, here's the difference. A centralized wastewater treatment concept, that's large scale. That's where you have a municipality or a wastewater collection system where that wastewater from the different buildings, homes, businesses is collected and taken to a central location, which is your wastewater treatment plant. Okay, that's centralized treatment. Okay, decentralized treatment, which is what a lot of people say, well, what on earth is that? Well, they'll understand what centralized treatment is. Okay, even though they may not understand the term or have heard the term, they'll say, okay, that's a wastewater collection system, goes to a central plant, gets treated, and then the treated effluent gets discharged, and the biosolids are managed. Well, a decentralized system, think small scale, think rural, think a bunch of septic tanks. It's all decentralized. Each structure has its own septic system. Um, so not only that, but a decentralized system could have a small plant treating a few buildings. Like I told you, the Glorieta Conference Center, if you ever drive east to Santa Fe on I-25, you'll pass by the Glorieta Conference Center off to the left if you're driving north. And that's considered decentralized because they have their own plant for those buildings there. Okay. They don't feed their wastewater to a collection system and have PECOS, for example, treat it. They treat that with their own plant. Okay. So that's decentralized. Septic tanks, decentralized. And so it's small scale localized systems. They treat wastewater very near to the point of generation. That's decentralized. So I wanted to explain that to you. Okay. Now, collection, centralized wastewater systems, uh, it can be pretty expensive when you think about it. You have built up over time these wastewater collection lines that are going to take wastewater to a centralized treatment plant. Okay. So you got a collection network. It's the opposite of the water distribution network, where the water distribution network, we're distributing or delivering water to these homes, to these businesses. Now we're collecting wastewater and we're getting it away from the homes or businesses to a treatment point. Okay. So this can go miles and miles of collection line. Okay. So that's a centralized collection system. Decentralized, not a whole lot of piping. Or collection points or network nodes. It's basically you're focused on uh, on-site containment and package plants, treatment on site. So you're not going to have a whole lot of collection lines. You'll have a few, but you're going to go into the hundreds of feet, maybe even thousands of feet, if that, rather than hundreds of miles for a municipality's wastewater collection system. Okay. And you'll hear for decentralized systems, you'll hear of septic tanks, package plants, that kind of stuff. So that's the difference. I wanted to just explain that to you because I'd mentioned it. And what I hate is when somebody talking about a topic mentions something but doesn't fully explain or assumes that people understand automatically what they're talking about. This is a review course, but I realize the majority of you in here are dealing with a different waste system, waste treatment system. So you may not have heard this. So I wanted to explain that to you. Okay. Going on a little bit, the ideal applications for a centralized system, urban centers, municipalities, a large city that has access to public funding and a revenue via utility bills. They can handle the maintenance and the operation and replacement of those lines with that money coming in. Decentralized, very low density residential areas or populated areas. Okay. Campgrounds, schools, isolated residential subdivisions. Okay. That's prime candidate for a decentralized system. A centralized system, ka-ching, it's either built up over time, or if you're putting in a subdivision or expanding a network, a wastewater collection network for a municipality, for a new subdivision or area that you're annexing, what have you, that's a lot of upfront money that you got to spend on capital projects, on installing the collection lines, on rights of way, on lift stations if they're needed, manholes, what have you. So a lot of upfront costs for per gallon treated. So somebody's going to foot the bill, either a developer or a grant, or typically utilities don't want to use revenue from existing customers for a system expansion to include others, because they're getting the existing, if they did that, they would be getting existing customers to pay for somebody else's bill. So that's something utilities typically don't do. It's more okay, who's reaping the benefit? Whoever's reaping the benefit, that's who's going to pay for the upgrade, is typically the way that works. Okay. Decentralized system, not a whole lot of upfront costs. You could get somebody with a backhoe and trench some pipe, PVC pipe, lay down some bedding sand, and then compact over that. You can put in some really quick inexpensive fiberglass manholes, put a collar around them, put a cap on them, you're good to go. Okay. Um, so this is something you're going to see again in the rural areas. It's when you don't want to or can't expand municipal sewer lines or run a municipal sewer line to collect wastewater from a new subdivision. Let's take, for example, the village of Glorieta. Okay. Glorieta actually has its own sewer association where they have a package plant that they're managing. And I think the long-term goal is for Glorieta Conference Center to get onto that system and do away with their package plant. If they haven't already started moving in that direction, they're heading in that direction. But the idea here is, let's say Santa Fe was closer to Glorieta or closer to Pecos, it would still be difficult for Pecos or Glorieta to run a bunch of wastewater lines to the city of Santa Fe system. And, you look at all that rock in the area, you look at the terrain, it may not be physically possible. So even if we had like a subdivision near the city of Santa Fe, if it was impossible due to geological reasons, due to costs, to run that wastewater system to the city of Santa Fe's municipal system, then you would be looking at a decentralized wastewater system. An even better example would be the village of El Dorado. Okay. El Dorado does not have centralized wastewater collection network. It it doesn't have a centralized plant, so it's decentralized. While it has a water distribution network where the El Dorado Area Water and Sanitation District pumps groundwater out of wells, and they're working on getting a connection to the county system, so they'll get water from Buckman Direct Diversion via a network, a transmission line. They get that water from a distribution network. They have septic tanks out in El Dorado, is my understanding. They are looking long term at putting a sewer collection system out there, a wastewater collection system, and a plant out there. But that's a lot of money because those homes in El Dorado are spread out. Alternatively, they could wait for the city or county to extend wastewater service out there, but I don't see that happening because the amount of line that would have to be taken to get El Dorado's wastewater to the city plant or to a county plant near New Mexico 14, that cost way too much money. So El Dorado is stuck with, for practical purposes, they're stuck with a decentralized system. Okay, so that was a bit of a side note there. I just thought you guys might want to understand the difference when people talk about a centralized versus decentralized wastewater collection system or wastewater system. Let's go back to our lecture now, please. Okay. Well, I guess we're not. So one more slide. I hope this is the last slide I put in there. Resilience and risk. So centralized, there's a single point of failure. If your plant breaks down or pipe ruptures, a big interceptor taking a lot of wastewater to the wastewater plant ruptures, oh my God, you are going to see a lot of people get really upset. For example, you may know, and again, this is not me trying to beat up on the city of Santa Fe's wastewater management division. I know a lot of those folks, they do the very best they can do, but they are dealing with an older plant that past management may not have focused on and may not have set aside enough money to maintain. So you may have read in the paper over the past several years, E. coli discharges, different types of problems at the wastewater plant. Think about that. If that wastewater plant went down, there's one wastewater plant for the entire city of Santa Fe. If that one wastewater plant went down, people aren't going to stop doing their business or flushing or what have you. That wastewater plant, that sewage is still going to keep coming. So they're going to have to figure out something very, very quickly to get that plant back up online. But could you imagine if they couldn't get it back up online? Regional environmental crisis, because people aren't going to stop pooping or taking showers or what have you. That inflow is still coming in 24 hours a day, 7 days a week, 365 days a year. Okay, so that's what I mean by a single point of failure for something like that, widespread environmental and public health crisis. Okay, decentralized. Okay, so you've got a bunch of different systems all over the place, like septic tanks. So if one localized unit fails, it doesn't threaten everybody else. Okay, that one person is going to have a mess on their hands if it's septic, or if it's a small package plant, they're going to have to do something. But a small package plant, there are places like one company called Rain for Rent out of Durango, Colorado. They pride themselves in being able to provide emergency, low cost responses for equipment, for pumps. They can provide, for example, for a water treatment system, they have and can get a hold of reverse osmosis water purification units that are on semi trucks. They'll truck one out to a community, rent it to them, lease it to them, and they'll let them treat their water. They'll do the same thing with small package plants for smaller communities. Okay, they're temporary measures, but those are quick responses. But the city of Santa Fe or any other municipality, not trying to pick on Santa Fe, any other municipality, a big regional plant like that goes down, oh my Lord, you're going to have a mess on your hands, a public health mess and environmental mess. So that's what we mean by resilience and risk of these two different types of systems. Okay, so we're going to wrap up this lecture, and I'm going to give you a to-do list. Um, it's not my intention to give you guys busy work just for the sake of making you or keeping you busy, or making you suffer. The idea here is uh, your employer and you, as students and employees, you wanted a review course. The idea behind the review course and the material I'm giving you is to help you get organized, help you get to the material, understand it, and study for the exams. Okay, so here's what I want you to do. I want you to look at the efficiency formula and those three loading metrics: the weir overflow rate, the surface loading rate, the solids loading. And I'm going to give you a separate lecture on those. Understand what they are. Watch the lecture. Okay. Those are level 3 and level 4 exam questions. You understand those, you're going to save yourself some time and heartache on the exam, because if you can get to those, you can do them. Hey, points in the bank, right? Money's in the bank. So I want you to understand those. And the efficiency formula, level 1 and level 2, I want you to understand those, okay? Um, for the level 1, level 2 examinees. I want you to understand those percentage removal rates that we talked about that I presented to you that are also in your manuals. Understand those, okay? Understand how to manage, how to deal with sludge blankets, both the primary sludge and the primary clarifier, and the secondary sludge or return activated and waste activated sludge in the secondary clarifier. Okay, understand the difference between the two sludge types. Okay, between the two clarifiers, the primary and secondary clarifier. Okay, for your level 1, possibly level 2, but mainly level 1, or your small system, if you decide, oh my God, I love this so much, I want to be a small system operator and get certified. Understand the Imhoff tank, how it operates, the fact that gases are going to escape off the side and not bubble up through the into the sedimentation basin, and then understand on the combined unit, the clarifier and digester unit, the combined unit, there's a boot seal that's going to prevent that gas from going back into the clarifier sedimentation portion. Okay. Once again, I'll stress this. Review the chapters, chapter 2 in the Environment Department Study Guide, and I want to say chapter 15 in the Ragsdale Manual, the safety chapter. Easy, low-hanging fruit, money in the bank, points in the bank. You do that, you might put yourself over the top. And if you pass by 1 or 2 questions and you look and you say, oh my God, I did really well on safety, well, that just puts you over the top, made you a certified operator. And as you've seen by my level 3 results on the wastewater side, I passed by 1 or 2 questions first time I took it. I don't say that to brag or because I'm proud of it. I'm just trying to tell you that whether I had gotten a 100% on that exam or a 71.67%, which is what I think I got, I did what I needed to do to become a level 3 operator. That's what I'm telling you guys. I want you guys to do really well on the exam to feel comfortable going in. But whether you pass by 1 point or 20 points, as long as you pass, that's the important thing, okay? But that safety stuff will put you over the top. Trust me on that. Low-hanging fruit. Don't let it slide away, okay? I want to remind you what we're looking at on these different levels of exams. For level 1, the material is going to focus on general knowledge, on safety, and on routine maintenance tasks. Okay. Think about where a level 1 person is in a municipal wastewater plant. They're doing sampling, they're raking off the bar screen, they're taking a sample of sludge in the primary clarifier with the sludge judge. They're doing a lot of that, but they're also focused on safety. Okay. Level 2, you should start understanding the biological cycles we're talking about. And you're going to have some simple operational math. You're going to have that on level 1 as well, but level 2, you're going to see a little bit more of that. Percent efficiencies, that kind of stuff. Okay. Level 3, 2 words, activated sludge. And this one, they're going to want you to know process control and how to manage processes, how to troubleshoot processes, and they're going to want you to do loading calculations. They're going to want you to do disinfection calculations. They're going to want you to do what's called hydraulic calculations, pump calculations that we'll go over later, as well as calculate of energy or electricity needed to run a motor, which runs a pump, which moves water. The pounds formula here, that's probably, I put a lecture on, a YouTube lecture on your last module that said, read this, watch this. It's a wastewater operator that goes over the pounds formula and what's called the Davidson pie chart with you. I'll do that as well with you, but watch what he has to say. He explains things pretty well, and it's more an operator to operator explanation kind of thing, so that'll help you. The pounds formula, it'll save your bacon on level 3 and level 4. Okay, it really will. Level 4, you're talking regulatory issues, nutrient removal, and management tasks like putting a budget together, budget calculations. How much chemical do we need to buy, and what's going to cost us for this process if this is our wastewater and this is our disinfection process? How much do I need to set aside to run a pump station if a pump has these characteristics, and this is what the cost of electricity in kilowatt hour is? And this is how long the pump's going to run over a year. They can ask you, what's it going to cost to run the pump for a year? Okay. Here's what I want to put aside for you right now. Don't let any of this intimidate you. You've taken the first step. You're taking this course. You're reading the manuals. You're doing the homework. Okay. Those are key. Don't blow any of this off. I know it's summer. I know you want to go fishing. You want to spend time with the family. You got time for all that. But spend an hour or two every couple of days going through this material. If you need to spend some more time on it, spend some more time on it. This is important. Okay, this is your career at stake here. This is going to help you move up, and it's going to help you understand a lot of things just from a professional perspective. Okay, I have posted your homework set. Okay, it's 28 questions. It's a little more than normal. I'll probably dial it down the next module because I want you guys to have a good weekend, a Juneteenth holiday coming up. But if you got questions or comments, please put that in the discussion thread saying ask your questions here for module 7. Feedback, please. Please fill out the weekly feedback quizzes. I want to know what's going right and wrong for you. I want to know what you're learning. If you want to say, you know what, oh my God, you lost me on this lecture, you were full of doodles, say so. You're not going to hurt my feelings, but I got to hear that to adjust so that you guys do get the material you need. Please work through the assignments, get the feedback quizzes. And it's not a 20 question assignment. I increased it to 28. The reason I increased it to 28 is I included math problems for every single level for you, okay? Start looking at the math chapters in both the Environment Department and Ragsdale Study Guide. I prefer the Ragsdale Study Guide for math because he just wrote it in such a manner that it's just crystal clear. So take a look at the Ragsdale Study Guide for your math problems. Start doing that now. Don't wait until we hit the math chapter. You can look at the Environment Department Study Guide as well. That's no issue. But by all means, do look at the Ragsdale manual, okay? I'm going to post another video, like I said, and we're going to cover the surface settling rate, surface loading rate, solids loading, and weir overflow rate. And you're going to see these on your weekly assignment. Okay, so please stand by. I'll get you another lecture that'll walk you through the math problems of these three metrics. And if you got any questions, please feel free to ask. Thank you for your attention.